being soft with a good jacket.
Yeah.
Okay, I'll be back.
I really miss fans.
Yeah,
Sorry?
I really miss fans.
same to me.
Do you think about this?
I think it's the first one. Do you? Like the we had to find an error in one of them, right?
Okay.
The first one is like it. I don't know how to explain it, but there is a long time between the time they pour the water and it starts flowing. I don't
Yeah.
know. How do you think about it?
Yeah.
Okay.
Yep.
So I agree with it. Yeah. And the other thing is when the water starts flowing, it's just
Yeah, it's like
Interesting.
So is everybody made a perfect model?
no.
Okay, so let's go through the movie and let's have a look. If you understand the story. Do you watch the movie?
Yeah.
Yeah. Yeah, so what about this one? It's almost the best one, I think. So obviously it's running. What do you think? Where is the trick?
So I think that there's a separate flow of water in the pipe. Like the pipe has its own individual flow initially in the first round. So there's like another additional valve connected through the stand maybe.
Yeah, some pump, hidden pump.
Yeah.
Where is it? Yeah.
Either in the base, which is like connected through the pipe in the lower part of the stand.
So you can hide a lot of beer. And
Yeah.
I think it's here this first off.
Okay.
It's amazing that it's enough to have this little
Mhm.
thing. It's the only thing I can think of. Because there I don't think so. Because there I don't think this is just a little thing. But I think the pump is in here, and it's this kind of peristaltic.
Oh.
But it's weird that.
I thought there's like an external flow through the stand, like the clamp, the second clamp at the bottom.
Which one?
So
Show me.
So, like when they first start pouring the water, I feel like the water gets stopped somewhere on the table.
Yeah.
And then another flow like pushes this water out. Like at least in the
Maybe that they have another.
So I feel.
Well, if there will be another flow, then there will be an increasing amount, right? So,
No, that's only to like just enough to tip this over. Like a little amount just to tip this over.
Yeah.
So that's why when like in the initial part of the video we see that even though there's a little bit water trickles down, it's mostly just pushed up.
let's go back. Let's see it again.
Yeah, look, so this water just starts moving.
Uh-huh.
Yeah.
But where is the pump? Where is it?
Then I feel like there's a pump over here that it pushes
Here, from there. Yeah.
behind the car. Yeah.
Okay. This is the coolest one. On the other side. Okay.
I think it has a motor.
Yeah.
There's a motor, yeah, and it's easy to hide it.
Yeah.
So there's probably a rotating wheel
Yeah.
here with the motor. Okay, fair enough. That was easy. I think it's
I think it's made in a way where it tries to show that this big wheel rotating is making it rotate, but actually it's the other way around.
this one, yeah, exactly. What is it? I think there's nothing in here.
Yeah, I think this can work.
Still work, except, right? Except, I think the basic trick here is so it looks like all these wooden things are the same size, but they're not, right? They're getting smaller and smaller and smaller. So there's no trick here, except maybe a visual trick that I think the way they arrange it, they look the same size, but they're not. This one is lame, right? You can't even see what's behind.
Yeah.
Alright, fair enough. Very slow. I like this one. It's an additional fun part. This is my own. Sometimes you don't see what's behind it. Like when it kind of tries to show you the amount of this thing, it doesn't work. Okay? I put some out there. Someone's personally saying that. It's the thing that's not true. But I like it.
Kind of like it's like the classic magic effect, where the attention is something to the
And I think here the clear probably meant something on there. Maybe on the stage. Okay. So it's fine. Alright. Mechanics. So we did thermodynamics last time. Do statistical mechanics. And I always try to kind of motivate you, right? So once you get better motivation, then we go through all the giants that actually founded statistical mechanics. And it turns out like a very interesting thing, and I think this is very special for statistical mechanics. It's very dangerous to do it. Quite a few people ended their lives prematurely. So let me just walk you through this. So Robert Meyer, the guy who formulated the first laws of dynamics around 1850, he just jumped out of a circular window and ended up in an asylum. Ludwig Boltzmann is probably the most famous one. This is, by the way, his grave in Vienna. If you're ever in Vienna, it's the central cemetery, and above his bust there is this famous entropy law. So he hanged himself, and apparently, so this is an interesting story because when he came with his statistical mechanics and kind of the atomistic explanation of thermodynamics, people were criticizing him very heavily because
at that time the atomic theory was not generally accepted. They were saying, hey, why do you bring this concept? Nobody has ever seen any atoms. Matter is continuous. And he was very frustrated, and he's essentially people didn't accept this theory. And it could be part of the reason why he was depressed and actually committed suicide in 1906. And remind me, photoelectric effect, the ultimate proof actually that there are particles, right? That was 1905. So it was only like a few years later that it was obviously clear that the atomistic theories should have been. Polar and phase transitions. Yeah, that's a really sad story. I mean, he shot not only himself but also his daughter. 1933. William James. So the foundation of thermodynamics. Nobody knows, but they found him there. Fritz Haber, a very important chemist. So he didn't commit suicide, but his wife did commit suicide, and his son and daughter committed suicide. He did other bad things. He invented poisonous gases in one month. So interesting. Gilbert Lewis, 1946. So the Lewis acids and bases. So the story goes that Gilbert Lewis was, I think, 45 times nominated for a Nobel Prize. Never got it, and then for the 46th times he was nominated, and he got it the next day. He was fired. But some people say it was an accident. So, and the last of course, Bridgman, high pressure physics. So, okay, so just like in thermodynamics and statistical mechanics is fun. Yeah, who's excited to study thermodynamics? And being a little bit on this, we have Halloween, right? So it's almost like a Halloween. If you ever in New Haven, next to the Yale University, go to the cemetery. I haven't been there, but I think I want to go there this time. So that's where actually Onsager and Kirkwood were professors, and they were like the founders of modern statistical mechanics and non-equilibrium thermodynamics. And so Kirkwood died in 1950. They didn't commit suicide, they just died from and Kirkwood died first, and then they put the gravestone, and just all these things like all these merits, a professor in chemistry, all the prizes, blah 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 blah. It's like if you medicine there, right? And then some years later, Onsager died, and all they put there was like Nobel laureate. Interestingly, and that was there for a long time. And then 1991, Onsager died 76, and his wife died much later, 1991. And when they buried her there, like the kids noticed that this is not fair. Kirkwood has all these prizes and everything, and Onsager only has the Nobel Prize there. So they actually put this asterisk there, and it says, etc. And that's a true story. And another true story about Onsager is, so he was Norwegian by origin, and you will need the name of Onsager if you do the models of dynamics and statistical mechanics. And he moved to the United States first he moved actually to Brown University, and they hired him as a lecturer. And after one semester, his colleague said, I won't say he was the world's worst lecturer, but he was certainly in contention. He was difficult to understand anyway, but he also had the habit of lecturing when his back was to the students like this. And he was writing on the blackboard, and nobody could see what he was writing. To compound matters, he was a big man, and students had to be around him just to try and see what's being written. So sometimes very good scientists don't have to be good teachers. And so he was teaching statistical mechanics, and he had two courses, 1 and 2. So the students renamed the first course Statistical Mechanics 1, they renamed it Statistical Mechanics. And the second one they renamed Norwegian 2. Also English wasn't very good. And he only lasted like a couple semesters, and then they essentially fired him. But then they later hired him at Yale, and they never let him teach again, so they just sent him to science. He got a Nobel Prize.
I also like how the next para starts with his problem in communicating with lesser mortals.
Yes. He assumed that he knew that everything was good after money. Yeah, right. So,
Anyway, so much for intro to stuff. Let's do a little bit of it. We're last time we did thermodynamics, that means phenomenology approach, but we live in modern times and we want to go atomistic. We want to understand the things from, say, first principles. Okay, so where's the lesson from that? Okay, now I should be like on Saturday. Okay, okay. Maybe I get an overpriced then. So maybe one way we can formulate it is that it's like a microscopic thermodynamics. So like I told you, the thermodynamics started with a steam engine, the big objects, right, and trying to understand the properties of large systems. Now we start with the small objects, with the atoms, but still we want to get to the properties of the large systems. So maybe we can call it like microscopic thermodynamics. And the idea is we want to get thermodynamic properties thermodynamics properties from properties of atoms and molecules. So from atoms and molecules. In other words, we need to know how atoms and molecules interact with each other. So we need to know the intermolecular potential. Force field, if you wish, in molecular dynamics. And using tools of statistical mechanics, we will get thermodynamic properties of the large system. So energy, free energy, entropy, etc. Okay? So that's essentially the machinery that will allow us to go from, if we know the interaction between the atoms and molecules, we can pull out some dynamic properties. Okay, so some basic definitions. We will be using. And again, this is not just a futile exercise, but when you will be doing molecular dynamics simulations and analyzing a trajectory, eventually what you want to report on are the thermodynamic properties of your large system, so you will use the language of statistical mechanics. So we need to know the basic terms. So one of the basic terms is system. So what is a system? It's any entity you're trying to describe, any set of molecules and atoms, so any entity you're describing. And to connect to thermodynamics, in thermodynamics, the equivalent would be the microstate that we talked about last time. Okay. Another thing we need to define is coordinates. Okay, so this is a set of independent parameters